Vamos a empezar. Son las 3:05. Nuestra usual. Pongamos acá. You go? Hello, everyone. Welcome back to a new session of the Chiara probability seminar. It's for me a real pleasure to introduce you to Mira Shevchenko. She comes from Mira Shevchenko in Nice. She will tell us about fractional interaction particle system, in particular about drift parameter estimation. All yours.
Yeah, thanks a lot. Thanks for the invitation. I'm super happy to be here. And you guys, I'm sorry, it will be a bit technical and I try to motivate a little, but yeah, it's mostly probability. Yeah, a bit technical. So yes, I'm presenting a recent work joined with Chiara Amorino and Nourdin. And so let's see what I'm talking about. Maybe I can pay here.
Let me help you. More.
Okay, perfect. Yes.
Maybe it's not working anymore. And now.
Okay. So the model is going to be, as said in the title, the interacting partial system driven by a noise that is called the fractional Brownian model. So what is an interacting particle system? In very simple words, it is a generalization of a stochastic differential equation in n dimension. But the point is that we also have a dependence on something called the empirical measure. And the empirical measure is simply defined as the sum of Dirac measures of the different values at a certain time t of the process that we want to observe, and the sum divided by, so it's the average over all the positions. And so we want this dependence to be in the drift. Is here the Vm. So we have the following structure. We have the sum, finite sum of different functions Vm, and they all have a multiplicative parameter theta m. And so in this drift, we have the solution itself, and we have the empirical measure. And then we have the noise, and the noise additive fractional dph, and we have IAD code. So this noise, so I from 1 to n, generate us our system of equations, different times. And our time t lives in a propagation of 0 to t, and this big t is constant. It's just going to be some number. Here we assume that h is larger than half, so the Brownian motion that has the long memory property. Yeah, I recall maybe that this is a generalization. Indeed, this is a process that depends on some parameter h between 0 and 1. And if h is equal to 1/2, this is exactly the Brownian motion. If h is larger than 1/2, then the increments have strong dependence, positive dependence. This is how you can imagine this. Okay. In our estimation, so I talked about parameter estimation. So we suppose that we know everything about our noise. We know the sigma and we know the h. And we are going to observe the entire trajectory. So even if they are not known, on a finite interval, we can exactly recover sigma and h via power variation. So this is you can also suppose that they are not known. This is not a problem. What we're interested in is estimating the drift parameters, namely these theta m here. Suppose that theta lives in some subset of Rp, and we want to estimate this vector. And as I said, we observe the trajectories of our process x in a specific interval, large t, and the asymptotic is in n. So we let the number of particles go to infinity. Okay. So just to show you a bit what it can look like, here is a simple example where the dependency on this measure, and you remember this is the empirical measure of your process, is the expressed as an integral of some function du. So for instance, you will have, or I mean here, you will have a dependency on an average of f of xjn. So for instance, here you would have something like this case here, where you have x, and then you have the average of all the xjn times some parameter alpha, and then again, everything is maybe times some theta. And this is a simple example to show you the difference between no interaction and, I mean, this type of interaction, for instance. So if you have no interaction at all, if this dependency on the different xj's is not present, if your alpha is equal to 0, well, what do you have? You have copies, independent IID copies of fractional Einstein-Lindbergh process. Ergodic, it's mean reverting, every trajectory kind of fluctuates a bit and goes back to the mean. So this is what it looks like. But then if you have, for example, your interaction with alpha equals 2, well, what you can see is that if this guy here is negative, then if the particles will get closer to the mean, actually we will have a trajectory that will start exploding because we'll have something positive here jointly. And so there is a slow change of behavior from something that starts as the normal Einstein-Lindbergh process, but then explodes when the mean starts exploding. So there is really a big quantitative difference in this interaction term. And of course, this is just one example. I think of many more. Okay, so what are we going to do today? I will tell you why we are interested in this model. Why are we considering this? I will tell you what we know already, what we are building. And then I will tell you how to deal with the problems that we have, how to construct the estimators, and what we can say about these estimators in terms of the theory. So, for statistics, it usually means consistency and asymptotic normality. Give you some ideas of the proofs, and then show you a bit more pictures and present somehow a perspective. What are we doing now? What will we do later? Okay. So iterative particle systems. This is a little shout out to the applications. It is you can see that in every scenario where you need to encode interdependencies between objects. So for example, when you have different people that want to vote, for instance, or that want to agree on something, you have a population of Valparaiso. One person will influence somebody else, there are people who influence more people, so there is a dynamics of opinion with respect to that can change. For example, if the average person thinks something, it will kind of influence also the opinion of individuals. You can have this in biology, when you model, for example, epidemics, how the mean state of the system will influence the individual getting sick or not. Interactions of neurons. This is actually something coming from the discussions where we talk that in fluid dynamics this appears because the particle velocities seem to also depend on the mean state of the system. So you can find this there. And of course, in finance, you have all kinds of mean field games type scenarios where also somehow the average state matters. So, okay, this is interactive particle systems. Of course, if you're a probabilist or if you're somebody who works a lot with probabilistic models, you want to give some noise in the mix. You want to say not everything is completely deterministic, but there are some fluctuations. But usually you have a Brownian motion that governs this noise. But sometimes you would like to add also memory to the perturbations that you give to the noise. And you can think, oh, maybe you know from physics that you have an interdependency in your noise that you want to encode. Or maybe you just observe the dynamics and you realize, oh, they are very smooth. They cannot be governed just by the Brownian motion, or on the contrary, they are very rough. And so there you start thinking, maybe you have positive correlation or negative correlation between neighbors. And this brings you to thinking, oh, maybe I can model something with fractional Brownian motion instead of the Brownian motion. So this was the motivation for us. For Chiara, who is an expert in interacting particle systems, and for me, I am more coming from the fractional world, and Ivan, of course, knows everything about everything. This is how we set up, and I mean, when you look at the interacting particle particle systems, the ideas, the field, etc., is known for quite a long time. But the statistical inference, even driven by the Brownian, is very recent. So you have a couple of early contributions in the 90 and 2011, but here you can see the bulk of the literature all coming from this decade, actually. So there is a lot for Maxwell-Blassov equations. These are kind of the limiting equations when the number of particles goes to infinity. There is a beautiful contribution by Dellameister-Hoffman for a non-parametric estimation of the drift. And there are some more specific cases considered, specific types of estimation problems addressed in these further papers. The usual asymptotics for this is that the number of particles to infinity. And of course, I will explain more in detail why you look at this asymptotics. And a lot of these proofs rely heavily on the fact that you're driven by Brownian motion, so you are in a martingale setting, you have a homogeneity property, and you can use this similarly to how you would do this for the FPs. Now, everyone who looks to the fractional processes knows that you cannot take the methods from normal SDs driven by the Brownian and translate them to the fractionally driven SDs. So there we went back and we looked at already the SD Brownian motion, because actually there was nothing, practically nothing on interacting particle systems with the fractional motion. And so we looked at SDs, and SDs, you have nice contributions from Clebson and Lebreton, and also the paper by Tudor and Biance that construct the maximum likelihood estimator for a drift like with us, depending on the linear parameter. And they use the representation of fractional Brownian motion with respect to Brownian motion to show consistency for actually any parameter h. And there is also the paper by Bertrand Torres and Tudor, where they look at the discrete version of the MLE for a specific process similar to the fractional Brownian motion, fractional random walk. And there are papers that introduce a different kind of estimator, namely something that is inspired by the least squares estimator, also for a linear parameter NRP, showing consistency, and in a specific case of the Ornstein-Uhlenbeck process, also asymptotic normality. But here, you can maybe see the E here is and why? Because actually to define the square estimator in the same way as you would for the Brownian motion, well, you rely on minimization of your least squares functional, and then what you get at some point is an integral with respect to your process. And if you take the integral, it's not consistent. So to say this, in this contributions, they consider the sort of the integral is you cannot get it from the data. You cannot discretize the observations and have some kind of Riemann sum to approximate your integral. So that's why estimator here is in a theoretical sense. And the proof here for the asymptotic normality is done with a heavy use of Malliavin calculus. It relies on the fact that we actually know exactly the distribution of your solution of the Ornstein-Uhlenbeck process. And there are a few generalizations of this, namely looking at an Ornstein-Uhlenbeck process with drift, with a deterministic part of the drift that is non-trivial, that has several parameters that you can then estimate. And for all of this, the asymptotics is in terms of t, so you let the interval go to t. Now, the transition between, for example, asymptotics for the Brownian motion so SD is in Brownian motion, and your interactive particle systems can be understood in terms of the transition between this t going to infinity and the number of particles. Because if your t goes to infinity, you can replace it by observing your first particle, cutting, and then continuing to observe it with the Markov property. And these two observations will be, if you like, two realizations of almost an identical process. So you can kind of see how this asymptotics is related to the number of particles increasing. Here, because we don't have this, this heuristic does not really work. Okay. So there are these contributions. Then there is an important part of contributions that treats almost interacting particles, namely these papers here, that treat a system of SDs with IID trajectories. And then you can show consistency and asymptotic normality. And you can also suggest, and this author suggested here, approximations of your score of the integral in the estimator, and these approximations are computable. We will speak about an analogous construction later. And finally, there are other contributions. There is the Lipschitz paper where they define discrete least square types estimator for a general grid, and also estimators based on identifying the invariant measure of the process. Okay, so these were kind of the entire list of literature with which we set off. And so now what we do? And here, I started with the parameters in RD, but here for simplicity, for readability, let's look at the parameter that is in Rn. So in the paper, the results are formulated in Rn. So how do we get to our estimator? We look at our error, if you like, and we look at the average over all the different particles, and we want to minimize this with respect to theta. Of course, this makes no sense, the derivative of x, but if you can formally write this down, what you get is a linear equation in theta. You solve this, and you get to this form. So it's average, and then the integral with respect to x of your drift, and here is the deterministic integral with respect to of b power 2. And here are your measures. And so, okay, you plug in your solution x in here, and what you get is theta plus, and then there is a remainder term where here you have the noise divided by the denominator. So like I said, there is a little problem, and the problem is this guy, we cannot get him from the data. He's well defined for h larger than a quarter, but yes, as long as we don't have exactly the integral, we cannot observe it. And so that's why this thing that I've written down, I don't want to call it estimator, but we call it an estimator in the paper. So what can we do to get somewhere else from this text? Well, for h larger than a half, what you can do is you can find the relationship between a Barkhouse integral and the Skorokhov integral. So this is your bad guy, and this is somebody who is nice, who you can discretize. And then there is this correction term, and that includes the Malliavin derivative of your process. This is just some process, yt, that you consider as the integral. And what is Malliavin derivative? This is another, well, process in two variables. The point is, it's also not directly observable from the data. But at least you can do the starting calculation, and well, you replace this integral here by this difference, so you get an integral that is pathwise, and your Malliavin derivative below. Yeah, like I said, same problem. Did we even get any further? Not so clear. So what we, and this is an idea that comes from earlier contributions, especially from the contributions by Nicolas Marie. So you look at normal SDs in one dimension with fractional Brownian motion, so this thing that's linear in the parameter. Suppose you derive with respect to the initial condition. Right? You have the derivative on that side. This guy is 1. This guy does not depend on the initial condition. He goes away. And here you have your chain rule. So b prime times the derivative of x. And suppose you do Malliavin differentiation. What do you get? The derivative of x. This guy does not depend on the fractional Brownian motion. He goes away. And what you get here is the same expression because it obeys the same chain rule plus a constant. But if you look at this guy or also that guy, what you see is just an ordinary differential equation, right? You have something equals 1 plus the integral of something with some additional term. You can solve this directly. And when you solve this for your Malliavin derivative, you get sigma times exponential of this integral here. And when you solve this for your derivative with respect to the initial condition, what you get is well, exponential of 0 to t, and then if you divide xt by xs, you get exactly the same expression. So what does it mean? It means that you can actually replace this guy by something that has at least a higher chance to be observable, because we can discretize this in terms of different initial conditions that we take. It's very nice. It's not true for the interacting particles, but we can show that it is almost true. Indeed, we can show that, well, you need to take the derivative in this first component, you add your empirical measure, you change things a little bit here, and then as n tends to infinity, it will approximately hold. So this is some hold. And with that, we can try to define our possibility. So yeah, there are some options to replace our bad guy here. And we do this first by considering two initial conditions. So for example, you have clinical trials and you start observing staying patients, but you start them from different, maybe starting dose, or some medicine that you give them or something like that. And so you have two neighbors. Then you can discretize the derivatives by, well, just writing differences between two neighboring conditions and dividing also by a difference. So this you can get if you observe two trajectories. These are close to one another. And this is here we can plug in exactly all of our observations. We can discretize this guy. We can discretize that guy. This is back integrals. We can discretize this stochastic integral. So we can implement this in it. And this is one. Another option, if you don't have two observations, what do we observe? We said that the Malliavin derivative was not only close to this ratio of two initial conditions, it's also close to this exponential of our derivative of the solution. This exponential has theta inside. So what you can say is, okay, theta, or so we hope, will be approximately equal this long equation with the theta. And this long thing that we just defined, we can call it Fn. And so, if our Fn is a contraction, what we can build is an estimator that will come out as a fixed point. So for every n, we can have a fixed point iteration, and I think n goes to infinity at the same time. We should get to the true parameter. So with some conditions on your drift, we can force Fn to be a contraction. Like this, we can define, well, either we do somehow our Fn in large n, in the number of particles, and we apply it small n times, or we can somehow, at the same time, reapply Fn and increase the number of particles. So these are two very similar approaches, give quite similar results. So we call this the fixed point estimator, and this is, I think later, I forgot to correct this, will be called iterative estimator. But two estimators coming from this idea. Okay. So we have actual computable stuff, 3 estimators, and we can now go and see, are they good or not? How do they perform? Okay. So the first ingredient is, okay, well, we actually have seen that our estimator with the Malliavin derivative is not too far from these replacing propositions that we made, because we have this almost equalities. So if we can say something about the phase estimator, it's already very helpful for our side, because then the other computable guys will be close. Okay, so we go back to the phase estimator. This is what the phase estimator looks like. This is the error we need to analyze. Here we have our stochastic integral. Here we have integral of d squared dt. Well, if only the trajectories were IID. If the trajectories were IID, we would be very happy, because we have here an average over IID random variables. They, of course, converge to something, because we have the law of large numbers. And the same thing will happen here. The expectation of this guy is 0, so yay, if only this were true, we would be done. Very fast indeed. But so how do we go from interactive particles to IID particles? Well, it's something called the propagation of chaos. In a very general term, especially for, I don't know, interactive particles driven by Brownian motion, but also it's proven for a lot of noises. What is true is that every particle, in some sense, converges to a solution of a different stochastic differential equation called McKean-Glashoff stochastic differential equation, and they converge together to IID. So using such equations. And the difference here, so this is the same D as we had before, but here we have this mu T bar, and the mu T bar is the law of our limiting process. So in the end, you obtain IID trajectories for n that goes to infinity of such a process here. Okay. So you only have to control how fast you're going with nice IID realizations. And yeah, for the fractional Brownian motion, for example, there are nice quantitative results established in Galeatti and Mayorkas, but they had considered a special case of B, namely something that is linear in the measure. So we did a little extension, because we have a Lipschitz drift, assumption on the drift, have some assumptions on the initial conditions. With that, we can show that expectation of the supremum of the distance between the two power p is bounded by something of order 1 over square root of n for p larger or equal than 2. So we can have a quantitative result concerning the difference between these two trajectories. So this is nice. With that, we can go directly to our denominator, for example. So these guys will get closer to the IID case. So you apply the propagation of chaos, and then you can apply the law of large numbers, and you get this convergence probability practically immediately. And so if that guy is non-zero, so if somehow the probability that the drift does not disappear is positive, then the limit of the denominator is also non-zero. Something that is that you don't have to study for. For the numerator, it is similar. There is a bit more effort because you need to control the moments of the stochastic integral, but in the end, you can get a convergence 0. So with these things, we can say, oh, okay, our fake estimator is a weakly consistent sequence, random variables. And this is actually even true for H below, beyond the 1. So for our noises, of course, this is going to be our non-computable. Okay, so what about the COT parts? Do we have something like that with some normalization, square root of n, that this goes to n0 and some values? Yeah, if you are in reality, things would be very nice, because this is just a classical central limit theorem. The problem is the propagation of chaos only provides a bound that is of order 1 over square root of n, so we can control the independent particles, but when we start controlling the distance, we get something that may or may not contribute to the limit. We don't know it. So there are papers saying that actually the propagation of chaos can be faster, but it is with respect to a specific measure, so it's not quite clear for us how to implement this here. But we found something else that helped us solve this problem. Maybe what we found is that the derivatives of our process converge faster than the process itself. So to address this so-called result, let's first look at whether we can compute the Malliavin derivatives, and then to see how far are they from one another. So, well, for s larger than t, the derivatives are 0. For s less than t, we have a difference between the derivatives with respect to the same component or different components. So if we have, I think it should be not equal here. Oh, no, this is correct. Yeah, this is for the limiting case. And here we have, well, if I equals j, we have this expression here. And if I not equal j, it's basically just 0. And for the interacting particles, of course, you need also to have an additional term that is there also for I not equal j. And so you have this entire longer expression, which also depends on the derivative in u of the drift. Okay. There is a previous result concerning the for h equals 1/2. There is a paper by Gonzalez Reyes and Weil saying that the derivatives of interacting particles convert to the derivatives of the limiting case, but there is no quantification of this. And what you could say is the following: under an assumption on the derivatives of our function b, we can bound the expectation of the supremum in the same component, so di xi as 1 or square root of n. But more importantly, if we have different components, so I and j here, we can have a bound that is very fast. That goes to 0 as 1 over n power p. Okay, so how can we use this? How can we use it to control our term? When we look at this term, okay, we look at the second moment of this term, expectation of this guy squared. Take out the sum, ij, and then you have the product of the two integrals, right? The integral in I and the integral in j. What you'd like to use is your path propagation of chaos for the cross terms, non-diagonal terms, right? di xj, dj xi. So you have a product of two integrals. What you would like to do intuitively is something like integration by parts. You want to swap this integral, bring it back as a derivative here, and take this integral and make it a derivative over there. And the nice thing is there's plenty of results like that. We found in the book by Biagini and others. And the result is the following. It says that this expectation here is an expectation of this diagonal term here. And then there is this extra term where exactly the thing happened that I just told you. You have di dxj and dj dxi in there. And then you have your deterministic functions depending on vs here and on h, and the same function here. And the main point is you have in all of the non-diagonal terms components that will go to 0 very fast. So that's great, because when the non-diagonal terms leave and we are only left with this diagonal contribution, this will be very close to basically the same case, but for independent particles. So yes, as written here, it behaves as n tends to infinity in the same way as the part where you have no cross contributions and you only have that term, and that term will be quite close to the term for the INA particles. Asymptotically, these off-diagonal terms do not contribute to the variance. So when you look at the variance of your total process, you realize, it is identical to this variance, and with that you can prove a sentence by controlling this extra terms. So with this, we have the following result. Under some renormalization, dividing by some constant that we can explicitly compute, we have a certain distance to the standard normal that we can control as n power minus 1 is 0 as n tends to infinity. And with that, of course, we have directly the asymptotic normality of the takes to me. Just plug in this expression, and then we have this convergence here. Okay, very nice. What about the others? What about the computable guys? So recall, what's the difference between the computable guy and the non-computable guy is this term here. So we need to control this term. And we need to see how this term is approximated. And in this Malliavin derivative of b, there are going to be Malliavin derivatives of x and here xk appearing. And again, we can use the propagation of chaos for all of these guys to bound the distance between the Malliavin derivative of b and only this diagonal term. And then we can base our approximation on the fact that we can show that this derivative differs from this short expression by something that goes to 0 fast enough as 1 over n. And the same here for the initial conditions. We can show that the distance is small. For the rate estimator, we can actually also quantify how fast our discretization step and should go to 0. So we have something like this. We know that this guy will be different from the Malliavin derivative by a term that is bounded by epsilon plus 1 variant. So as long as our epsilon goes to 0, we will have consistency. And then if our epsilon goes to 0, I think faster than 1 over square root of n, we'll have also asymptotic normality. Okay. Well, believe me, there was a slide saying this, but it's gone. Yeah. Maybe I can try the pen. Here you go. Yeah, so you need more assumptions, more technical things to control your difference. And then you have, yes, if epsilon is going to 0, consistency, and if epsilon is at least disorder, have a simple path. For the fixed point estimator, it's a bit more technical because you need to force it to become a contraction. Remember, this is the reiterated application of our large function, and you have an additional condition in your drift, and you need the maximal time to be bounded. But then you have this, indeed you get a contraction, and your estimators are really consistent and asymptotically normal. Yes, and so this restriction is okay because if our t is too large, we will be too small interval, it's okay. But the limiting variance here is a bit larger than the one of the ratio estimator. So this is somehow the price we pay for just observing one trajectory and not have calculations and then the difference between them and so on. So this is somehow the trade-off for us. And this one, for technical reasons, you only need in one edge. The ratio is in 2, and then this guy is in 1. The ratio is in p dimensions. This guy is in 1. Okay, and here is a small simulation study. We look at this function where you can quite clearly see what the interaction changes. Theta times 2 minus arctangents of x minus, and then there is this interaction term with maybe some parameter in here. And so you have alpha equals 0, you will get somehow a positive drift, but small, so you have some kind of a growth like this. It has different trajectories. And then if alpha, for instance, is equal to 1, then your x is pushed in the direction where the average is. And if it's close to the average, this guy disappears, and you just have a linear drift. So this is what you observe. It's kind of getting closer and closer to this linear growing behavior. And for that, we really did it by hand. We implemented our estimator. First, we did an Euler scheme, discretized our integrals, looked at the different derivatives that we take, looked at the iterations that we need for the fixed point. We got this result. So here's for theta equals 12. Here we have root mean square and the bias. So you see the terms are quite small. Different ages, they are similar, I think, and larger, of course, the terms get smaller. And for 2 dimensions, we took this linear drift equation. So we have here theta 0 and theta 1 and theta 2. For that, we also have results with a very small bias, and the root mean square error, of course, also goes to 0. So this was just a test and to see in practice that we didn't do something completely weird. Okay, so I'll put my conclusions. I think I kind of ran through everything. I think this is an okay time, I guess. So what we did, we computed on the base of least squares estimation idea estimators that were computable for the linear drift parameter estimation in our interactive particle system with fractional noise. The main new probabilistic tool is this quantitative propagation chaos shown for the Malliavin derivatives, which helped us achieve consistency and asymptotic normality. We have shown you a bit of numerical examples, and then there is a list of future work and work in progress. So in particular, we're working on this discrete observations with the general drift idea and the non-parametric estimation. So this students that started in October are working on this now, and they have my first results. But both of these cases are really difficult, each in their own way. We are very surprised because we thought that it's achievable, but it's quite challenging. And then the kind of more further prospects are looking at the rough case and also the multiplicative noise, some very, very first ideas, but we'll see how this goes. So this is all from me, and this is the thinking slide. Yeah, here is the thinking slide. And the thinking is
Thank you very much. Are there any questions here or in the other room in Santiago? Maybe we can. Yeah. Yeah.
Show video.
Okay. Go ahead, Joaquin. I think you can.
Can you hear me?
Yes.
Yes.
Okay. Hello, Mira. This is Joaquin. I don't know if you can see me, but how are you? Thank you very much for the very nice talk. I have a kind of theoretical question, or a bit abstract maybe, but it's something. I'm gonna mix the two notions of chaos here, because my question is: do you have some abstract characterization, or I would say, yeah, of a propagation of chaos? Imagine that you have some typically in propagation of chaos, you have like a triangular array of random variables which are exchangeable in law. So imagine you have that, but built on, let's say, n independent binary chaoses. Okay. So do you know if there is a characterization of propagation of chaos at the level of the binary chaoses? Because one could imagine that you will have the Malliavin derivatives that go to zero in some sense, the cross derivatives, right? But yeah. Is that a characterization, or I mean, because for instance, if you want to go to h smaller than 1/2, you will, if you have something which is less, let's say, computational but more abstract, maybe it's also easier to verify, or I don't know. Is there something in that direction?
I don't know if I understood your question correctly. So what you want is an array of random variables living in a specific chaos?
No, yeah. I mean, you have, because since you have independent, I mean, your fractional Brownian motions are independent. So yeah, you are constructing, well, some exchangeable random vector, exchangeable in law, on this n, it's an n-fold linear chaos, which
yes, okay, yes.
So do you think you can say, give some abstract characterization of propagation of chaos in that setting, but only in terms of what happens with the at the level of the Malliavin functionals, or the let's say the derivatives or something like that? I mean, because you show that what you're showing is that the cross derivatives go to zero actually, and you do it at some rate, but you use here the explicit expression in terms of the stochastic flow, so you know what to you go to do something which you know what it is because you know the expression. But is there some general result where you can say, you understand that? Sorry, yeah. I'm a bit.
So I guess what you could have is something like, you have a system of equations driven by a Gaussian process in general. I think for that, things should be similar, because I don't think we used anywhere that we have a specific fractional structure. Indeed, our example for all h from 1 for this cluster propagation of chaos. So I would imagine that this you can get for just a Gaussian process, it's creating a chaos decomposition. For which you can define the Gaussian variable calculus. You'll have to check this, but I think it's doable. For a more general process driving,
because here, for instance, you needed to go to the Malliavin derivative because you wrote the stochastic integral in terms of it. but
Yeah.
I mean, maybe it is enough, or maybe you need something to go to higher order derivative, let's say. I don't know.
Yeah. Yes, I don't know. I think that also what you need in our case, at least, is that you somehow have an understanding of the specific structure of your differential equation. You have to understand how your solution relates to the noise driving it. I don't know if you can have something like this but yeah, for general functionals, you first have to understand what you want to show in terms like which kind of statement you want to show in propagation of chaos. But for the differential equations, yes, I don't know if it would be interesting to look at higher order derivatives. Yeah, I'm not sure, but yeah, probably it will. You will also get propagation of chaos for higher orders. Yeah. I don't know if this answer is.
Yeah. Okay. Thank you very much.
Any more questions from there first to go in order? Okay, so here, any question?
If you compare with other kind of estimators, square or that kind of techniques, this is a better or more remarkable than
What do you mean for the least?
for the parameter that show is other kinds of estimation, square or in discrete observation without this technical practice.
Yeah, so for SDEs, yeah, I mean, it's a bit difficult to compare because here you have this advantage that you have really almost IID observations in a way. But you can compare the literature for IID, and there, of course, yes, you get similar results because you can show that patient cases is not enough to bring you back to SDE to IID cases. But yeah, technically, it's much more. Yeah, I mean, with IID observations, you have system says normality for free. But yes, I mean, and in terms of the definition, the ideas are very inspired by like the previous physics. These squares I did. Yeah. And this other estimation that you're looking at, this is a bit exotic. This is like minimal conference where you compensate the contribution of fractional Brownian motion. For the SDE case, for the interacting particles, we did consistency that looks very similar, but it shouldn't. Showing consistency, and it looks very similar to the SDE. We want to show asymptotic normality. There is a term that you probably will need to understand how to compensate. Not so easy. Yeah, again, I don't know if it answers your question. There's a lot to say.
Thank you for that. Questions? I have another one, probably pretty basic. You show us at the end essentially three estimators.
Yes.
And I think that in some sense they are so different kind of data.
Yeah.
Could you explain a little more? Like,
Yeah. So for one, so the main difference is for one, you need to have a very specific setup, which is you observe your growing number of particles, you observe for every particle sometimes t, and in parallel to this, you observe another system, but starting from an initial condition that is, a little bit different. Here you start from 0, and then you start from absolute. Have a small absolute. So this is something that in nature, it's not always easy to observe. Sometimes you can design an experiment with this in mind. Like I think medical trials is what people think of. You can choose which initial application or you can force this. In the other one, you don't. You just observe your trajectories. But you pay the price that it's computationally more difficult. You have to do this fixed point iterations to get to the estimator and the variance, the final variance. So this is time for the trade-off. I think this ratio estimator, the one with the initial conditions that are a bit different, it's a bit easier to define, it's also easier to program and so on. It's more somehow hands-on and natural. The fixed points, it's a bit more messy.
And about frequency of the observations for this estimator?
About what?
The frequency.
Yeah.
Frequency. With the example, like you have the whole path and you can sample us.
Yeah, so the theoretical results are for the whole path. We cannot quantify the discretization of how the frequency should be connected to the number of particles and such of the epsilon. So yeah, this really not.
Yeah, my final question was what did you say that there was no difference in the results when moving age?
No, not really. I mean, there is no difference. The thing is, the age appears in your limiting variance because the limiting variance.
Maybe you need to do it with
But I think I can spend a long time doing this because I want to go the estimator definition. Let's see if I can get them. The limiting variance is something like the expectation of this guy here. So here, to rewrite this, there is age dependency hidden in there, but in a very non-trivial way. So I think for different ages, it's not clear that this is monotone in age. And from the numerical results, we didn't see monotony.
But more than monotony, I think I understood that you didn't get any
breaking in behavior?
Yeah.
No, because I think because the schema observations is really more relying on localized numbers. So for different ages, the same. Yes, here two ages. Here it is smaller for a larger age. Here it is larger for a larger age. Depends also on the model, how the expectation will be defined. No, really.
Okay, well, we can keep talking later. So if there are no more questions here in Santiago or in anywhere, let me check in the chat.
Yes.
Maybe someone in either of the.
Yeah, you have questions. Not perfect, but I have something. Can you find that?
Well, no questions, so we stand again here.